All right, let's get the show on the road. When we left last time, we were dealing with the X-ray machine. We talked a little bit about the fact that we had this bremstrolity because the electrons coming in and striking the metal plate or what have you are not actually bound, and so they can slow down at all different fractions and give all different percentages of their total energy off of photons. So you get 1 photon, 2 photons, 8 photons, 15 photons a minute. If they give all of it off, then they'll give the most energetic and therefore shortest wavelength photon possible. The peak is roughly, for most, at least X-ray systems, is about a third of the max. So if you have 100 keV electron impedance max metal plate, if you looked at the peak of the X-rays they produce, it'd be about 33 keV. It turns out that most X-ray systems that are used in medical applications are used somewhere between about 0 and 100 keV. The lower they are, it turns out, preferentially by the photoelectric effect, the more sensitive they are to different types of material. But the lower they are, the less likely they are to pass through the body. The way you image in an X-ray system in a hospital is you catch the ones that don't interact, the ones that go all the way through. So if you make it too low in energy, they don't get through. That's why lower energy photons like regular light, I can't see through you. They don't have X-ray eyes. All right? So you have a trade-off between those two things, and that actually plays a part in mammography for women who are looking at trying to find very small breast cancers. These other guys here, the characteristic X-rays, they are not from the electron that's coming in slowing down. They are generated because you knock out electrons in the target material. So if you hit a lead plate, you'll get maybe a couple like this. If you hit a copper plate, they'll be somewhere else. So they tell you the target. So they have a totally different place from where they come. Now, in my notes, I found that there was at least one, I've actually found 2 places, but one that was definitely there on this section. Taking just simply what we know from freshman physics, if you look at the accelerator, any accelerator, basically all it is a voltage that applies a force on the voltage, creates an electric field applies a force on a charged particle and causes it to gain kinetic energy. That's what accelerators are. So television sets are accelerators. They came out of nuclear labs. Electron microscopes are accelerators. Ion implanters that make all of your semiconductors, they're accelerators. The way that we sterilize medical instruments is accelerators. The way we make plastics for shrink wrap, they're accelerators. There are literally hundreds of billions of dollars of industry based on accelerators. So in this particular problem here, let's see if I can find it. You've got a particle that gets emitted. Maybe it got emitted because you heated it, if it was an electron machine. Or maybe it was in there because you put a gas particle of some sort that you ionized. But somehow you have a particle with some charge Q. And then because there's a voltage, plus Q be here and say 0 there, there's a potential difference, which means that there's an electric field line like this. So there's going to be a force from that field line, that E. And that positive charge particle is going to want to go downhill just like gravity would push a mass downhill. So it's at higher potential energy, and when it gets down here, it'll be at lower potential energy. And that potential energy that's left will be going into its kinetic energy. So if you just sit down and do what we do in freshman class, and I could do it like this, the change in E is equal to the change in K, I guess I use, plus the change in U. But this is a conservative system, so there's no change in the total energy. Rearrange that equation and you get delta KE. It's going to be equal to minus change in U. That's the way to calculate minus delta U, because voltage is defined as change in potential energy divided by charge. That's how it's defined. So therefore, Q times change in voltage is delta U, and the minus sign comes from the fact that the minus occurred when you move the delta U to the other side. Now, the voltage was higher here. Let's say it's 10,000 volts. It's 0 there. So it goes, the final is 0 minus 10,000, whatever that V was. So you get a minus of a minus, and that's how it gets to be a plus V. So if you tell me the voltage and you tell me the Q, I can tell you how much kinetic energy it has at the end, because I'm assuming that it started with no kinetic energy initially, or pretty close to that. So what I need to know to find out how much energy the particle can give off is I need to know its kinetic energy when it's smacked into the plate. And I can find that if you would tell me how it was created. Now, you can give it kinetic energy by other ways, but this is the primary way because we have these things called wall outlets that we can plug into. So that's what we can do. You could say, hey, how did you get the particle if it's an electron? Oh, I gave it thermal energy to get it out. Okay, let's go back to thermal energy. If you give it thermal energy, like, 40th of electron volt, and I'm smacking it with, say, 100 keV of energy, I think I can ignore your 1/40th of electron volt. All right. Now, my error was that kinetic energy, if you want to make it in a single photon, should be hc over lambda, and I've lost a lambda. All right, so there should be a divide by lambda. And that's if you give it to the shortest wavelength. That's if you give it all of it in one step. So what this was simply a statement that I was giving all of that to a single photon. And all I was doing was putting in Einstein's equation there. If you take the lambda and rearrange it by moving it on top, put the kinetic energy on the bottom, and I just said that you can find the kinetic energy by that, you'll get this equation that they call the X-ray machine equation. Well, that's kind of a really stupid thing in a way, because it's nothing unique about that equation to X-rays. It's true for this particular machine, because it just works out that way. Okay? What it really is a statement of conservation of energy. All the energy can go to a single photon. I can give it energy by other ways. So they don't always give you the voltage, and they don't always give you the charge, and you can't just plug and chug. What you're supposed to figure out is find the energy by whatever physics you need, and then figure out how to convert that into a single photon. And that will be the shortest wavelength or maximum frequency photon you can have. Now, in most books, you won't even see the Q. Why not? They assume the Q was an electron. Did it have to be? No, I throw alpha particles and protons and carbon particles and all sorts of other things. Electrons are easy to do because the machines are smaller. So for some things, like making, if all you want to do is photons, an electron makes a good choice. So if you make it an electron, then Q now is 1e. If you had an electron, then Q would equal 1e. So we put 1e here, then that e would kill that e, and it would be 1240 volts times nanometers divided by the voltage of the machine. So if this is 100 kilovolts, you divide that by 100. If this is 100 kilovolts, you divide it by 100,000. So you take this voltage, divide it into that, and it'll give you the answer in nanometers. So it's an easy formula to work. If it was a doubly charged alpha particle, then you wouldn't have 1e, you'd have 2. But you still want to work in e, because you want to cancel the e's. You don't want to plug in 1.6 10 to the minus 19 coulombs, okay? All right.
Dr. Marble?
Yes?
Can you all see us? Because we can't see you.
Okay, I
We
didn't
don't see
know.
anything.
I can see you.
Okay.
You can't see me?
No, there's nothing on our screen.
Yeah, the screen is dark.
Okay, it's gotta be on your end, I can see you, just a second. We'll wait, let's call and catch you, just a second. I see 1, 2, 3 of you, a purple shirt and a black bag on the desk, and one walked out of the picture.
I know we can't teach modern in West Texas. They have like the cutest chick there. Like you wouldn't believe how cute that girl is.
What are you talking about?
The chick in West Texas, you guys ever seen that we took you in last semester? They have like the cutest chick in there. Yeah, like she came on camera.
Dr. Marvel? Can you hear us, Dr. Marvel? Okay, we disconnected, looks like. Hello?
Not even here.
Testing? Testing?
Can you guys see me yet?
Oh, can you hear us?
Oh yeah, I hear you fine.
Oh, okay. Well, we couldn't hear you there for a second. I guess we can just watch the video later. We don't want to drag down the class.
Well, sure, but we also want you to be able to give a thing. I want to make sure what I'm seeing is what's on the video. I sure would hate the video to be blank too. Anyway, what I was talking about was the fact that you got to be careful in the books, because books will give you equations that are special and for special cases. And one of the things they do in here is that they assume that the particle that comes in and makes the bremsstrahle is an electron. And that's not always true. It could be any particle that's charged that creates a bremsstrahle. And so what you need to do is calculate the energy of the particle and take hc and divide by that energy.
No, they're just seeing a black screen.
Not just divide by the voltage of the machine. If the particle has a charge of 2, the energy will be 2 times that. If the particle has a charge of 3, it'll be 3 times the voltage. It won't just be equal to QB. And let's see if I can find, well, of course it's in my notes, but it's also in your book on page 3.26, page 89. So on equation 3.26, they've assumed in that equation that the Q is an electron, that the Q is an E. And so if the Q was an alpha particle, if I put that on the test, you would get it wrong because you would use the wrong Q. So don't memorize the equation. Work through the physics from physics 1 and 2 to make sure you can do it.
Okay, if it doesn't, then I'll give you a call back. All right.
Please enter your conference ID. Press the pound key when complete.
Still see a black screen. Prairie View, can you hear me now? We seem to be having
It's always Fridays.
Yeah, but it's always my class and it's always Prairie View. I mean, I've run years and never had one class that I couldn't do this.
Yeah.
Well, at least it's Friday though, when you get out of here.
Getting ready to teach high school, this will not work nearly as well if that happens in high school.
No.
Prairie View? Can you hear me? Okay, now I can't hear or receiver.
They haven't come back yet.
Josh, are you an active writer? I just want to like sometimes I can't deliver here for black.
Okay, well, let's move on and maybe, hopefully, they will come back and catch up. And then if not, like they said, maybe it'll be in the video and they can watch the video. So, my point, to go back and finish one more time, my point is that there really should be a Q there in that equation in the book. When the Q is, when there's not a Q, when it's like just E, it's because they made an assumption, and that assumption.
Please enter your conference ID.
That assumption may or it may not be true. Can you see me now?
No.
I can see you, I can't hear you now. All right, so anyway, that's the point of that. Test your knowledge problems. Take a look at some of the ones I assigned. They should be fairly quick. The first one is just testing the argument about when do you get radiation and trying to drive home the point that you get radiation anytime you accelerate a charge. So the first one says, an electron is traveling in a straight line at constant speed. And the question you should ask yourself is it accelerating? What somebody on a test will ask is, does it radiate? They won't ask, is it accelerating? Okay? So if it's going in a straight line at constant speed, is it accelerating?
I might have to bring my journal today.
Yes or no?
No.
No. Does not accelerate. How do you know that?
Yay. Thank you.
No problem.
What was wrong?
Somebody changed the input on the channel.
Okay.
So it's not.
Maybe.
So can you see us now, Brady? Okay, so if the particle's going in a straight line at constant speed at obeys the law of inertia, it's not accelerating. If it's not accelerating, then it also does not radiate.
Can we mute the mic back?
So, no acceleration, no radiation. All right. Now let's put it in a uniform circular motion. So the thing, now I've got an electron and I'm sending that electron around in a circle. Is it accelerating now?
Yes.
How do you know?
It's a uniform circular motion.
It's a uniform circular motion. So what does uniform mean?
That
Constant.
means the speed is constant.
Constant speed, but the direction changes. So there has to be a force. So it is accelerating. And that means it has to radiate. So it's losing energy. Does anybody know what they call this thing? All right, if you don't, this thing is called a synchrotron radiation source. And they're very useful for building lots of devices. They can build micro heart valves. They're building micro air conditioning systems now. You can tailor-make the wavelength to any type of photon you want. I have a former student right now who's at Rice who's finishing a bioengineering PhD, and he's matching the wavelength to a cancer cell in order to do this. So these are synchrotron radiation sources, also known as light sources. There are very few X-ray and gamma sources that have only very specific energies, and they may not be the ones you want. If you get an accelerator and send it around in a circle, you can get anything you want, basically. You can vary the wavelength just by changing how fast you send it around in the circle. So in the old days, we tried to get these guys to speed up the electrons, and what we found out was, as we pumped energy in, they gave it away, and they wouldn't speed up anymore. So we've now exceeded to where you can't send an electron enough energy to keep making it speed up. So any of these big accelerators that are circular are not electron accelerators. You can't get them going fast enough. They'll give up all the energy. But on the other hand, it became useful because they became things that we could do engineering, chemistry, and other fields of science. So all those accelerator facilities still exist today, and people make money, but they make them as tools. So that if you go to, for instance, to LSU, there's a CAN-D light source that does exactly this. In fact, I think one of the things I gave you is actually pictures from that. And then, that is an engine block, and that is an ant.
Like an engine too.
Like an engine to make a micro engine,
Oh.
microelectronic machining. And that ant is the size of your piston, basically. All right? This is a gear. These gears are on the order of 500 microns. So we're talking about, maybe 10 hairs across. We make things smaller than that. That's where the world of manufacturing is going today. It's not about pouring a bunch of iron into a mold. It's about making machines that you can put inside the human body. You got to shrink, for instance, the size of a computer chip, that area goes down. Remember our Stephenville law? P over A? If you make the A go down, the temperature's going to go up.
Excuse me. I don't think.
Yes?
What material is those parts made out of, especially the gear?
Most of these are PMA, but you can make them out of a wide range of different types of material. They're usually of a polymer type or a composite, but you can make them out of other things. What you need to have is some sort of material that will actually interact with light, preferentially, so that you can either use the light to make a mask and then cut the rest of it out with an acid or some other processing material, but they make them out of a wide variety of stuff. In fact, there are national facilities such as the one at Berkeley that you can go to and bring your project and actually build whatever it is you want to build. Besides these guys, what I was saying about the thing with them being on a semiconductor especially is a computer chip. We can't keep shrinking them because the temperature is getting so hot. We can't use this P over A equals sigma T to the fourth anymore and keep the temperature low enough that it doesn't melt or redistribute the impurities inside the chip. We're going to have to build air conditioning systems in the chip. And that means building micro machines. So these are some of the things that the world is going to, which I find a lot of really cool stuff, not to mention it makes a lot of jobs for us. All right, so anyway, synchrotron light sources are highly useful things, and you'll find them all over the place. One that's more likely to be found in today, and not a physics lab, it's something like this. So you got an AC circuit. If you have an AC circuit, those charges go this way, and then the voltage changes, and those charges go back, and that means they turn around. And if they turned around, they accelerated. In addition to that, you're changing the voltage across them, which is changing the forces on them. So, yes, and yes. So what type of applications can you find for this? Well, one, it's noise inside your room. So if you've got a ballast above you and you've got a light bulb up there, you're going to have signal noise in any type of real sensitive information you have. You've got to be careful about that. In addition, if I make this, for instance, a very long big tower and run a wire up and down, it's called an antenna or transmitter. This is how you make radio and microwave and so forth. So radio, microwave, the energy leaves, you have to pump energy in. On the other hand, if I just have a wire here and I have an electric field that's causing a force to cause those electrons to go up and down that wire, then I have an antenna. It's the whole idea of receiving that signal. The only difference is the energy comes from outside in, and it drives it through my circuit rather than me pumping the energy in and transmitting it out. So I can either absorb it, and cause the electrons to accelerate, or I can accelerate the electrons and cause it to be transmitted. But if you get a charge to accelerate, radiation is involved. Always. Can't get around it. And the last one is one we've been talking about. If you take a particle and you shoot it into something like a lead plate, going to slow down through interactions. That means it's going to radiate. So again, does it accelerate? Yes. Does it radiate? Yes. These are the same questions. So the commercial application of that is X-ray imaging. You either to image something, either commercially, it might be to use this as an X-ray source to do tomography for looking for cracks in steel pipes. There are actual machines sitting at U.S. Steel, and they look in real time as the pipe goes down the line. Or they could be used as an imaging device inside a hospital, or you could be using this as a sterilizer to sterilize medical instruments. You can shine it on plastic and change how the plastic forms and use to shrink. There's one at A&M that does that sort of stuff. There is a wide range of things that such machines are used for. And then if you're an atomic physicist like myself, they're a problem because when you shoot an experiment, whether you plan to or not, and you have a sample there, it's probably going to hit other stuff and create background radiation you did not want that you'll have to remove. All right, I had a numerical problem on this particular set of stuff, I believe. Problem number 4. It says you had an analyzing magnet failure. This is often true. You have a magnet that's causing maybe a particle to bend in a device, and you happen to have this alpha beam, and when it failed, instead of making the turn like you wanted, it goes straight and smacks into your stainless steel pipe. So since it hit your pipe, it's going to stop. And since it's going to stop, it's going to radiate. And since it's radiating, you didn't want it to radiate, but you ain't got no choice. And what I'm asking you is, what's the shortest wavelength of the Bremsstrahl X-ray you can produce? So lambda min was HC over the guy here, which was the energy of my particle. So I'm going to give all the energy in a single step. And in this case, I know the energy right there. It's 2 MeV. So in this case, notice I'm not using the voltage because I was told the energy. Now that's 1240 MeV picometers. I'm sorry, not picometers, femtometers. Over 2 MeV. So lambda min is 620 femtometers. That's a very short wavelength. In fact, it's up near the gamma ray region. It's 2 MeV of energy. And that's going to be very penetrating, which means even though you may have had the beam hit inside a steel pipe, it is so penetrating it will come out of the steel pipe. And it can potentially radiate anybody nearby. So depending on how much beam and how much of this actually happens, you could have a potential radiation hazard. The things. Most people who run machines like I do of this sort have a Geiger counter nearby. Not because we ever expect to see energy, but just if something was to happen, it would set the Geiger counter off. In some cases, they're connected back into the console and shuts the machine down. In some cases, they just tell you to get the heck away from it. Questions about an X-ray machine and Bremsstrahl? Anybody here? Prairie View. Any questions about Bremsstrahl or X-ray machines? I see a shake of head no. Okay?
No, sir. No,
Okay.
sir.
Good. Those are pretty easy problems. So usually they're nice, easy things to ask, and they help raise your grade a little bit compared to relativity problems. So. Next thing, after we left that in the notes, there starts to be a discussion about the fact that not only can a photon carry energy, so you've got energy calculations, but a photon, even though it has no rest mass, carries momentum. right? We know that from electromagnetism. We actually found that back in physics 2. Electromagnetism and everything we find in here are consistent. So the equations that we can derive from Maxwell's equations and the equations that come out of Einstein's work here are the same. But it's a whole lot easier to get it out of Einstein's stuff than all those calculus equations out of E&M. All right, so I always can find that sort of stuff unless I'm in a class of E&M by using this stuff because it only requires algebra. What you can't do is you cannot use that rest mass energy equation because a photon doesn't have rest mass. By the way, when would a photon ever be stationary?
Never.
Never. It moves at c with respect to all reference frames. So the idea that you're going to set it in a frame where it's at rest and measure it is a meaningless thing anyway. All right? So be careful. You cannot use that formula for the photon. You would have C over C here. This thing is 0. It has no meaning. All right? This was derived for collisions of particles at mass. It was derived in finding the proper time reference frame. It does not apply to these photons. What does apply is this equation, which is always true for all particles. And so if you want to calculate the momentum of a photon, which has 0 rest mass and 0 rest energy, you take this equation, put E naught to 0, and you get PC, parentheses squared, is the square of the energy. Take square root. PC, political correctness, is equal to energy. Linear momentum is energy over c. I don't care how you memorize it or remember it, but the bottom line is this always works. This was derived under specific conditions that M naught was not 0. So this is the one that gives you the correct equation. This is really useful for photons. And we'll use it to derive some other formulas. And the other formulas, however, are more fundamental, in fact, because they occur and are true even for particles that have rest mass. Where, for instance, Einstein's equation for energy isn't true for them, and where, in fact, they don't travel at c. So this one's really useful for photons. Usually people tell you the energy of the photon, and then you have to calculate the momentum, and all it says is take the energy, like MeV, and divide by c. So if it's 3 MeV, it's 3 MeV per c. That's about as easy a calculation as you can get. Change the unit. If you want to change it to something else, you can use Einstein's energy equation and plug in up here for E. And I don't care if you want to use, I use H nu or you prefer HF. All right? So, depends on the textbook which one it has. So P is HF over C. If you know what frequency, then you can use this equation if you didn't know the energy. Personally, I think memorizing so many equations is a waste of time. If you know the first equation, you should be able to find everything else. What is kind of useful is to derive C. If you take this equation here, then you can do some substitutions and rearrange it a little more. You can take for V times lambda, that's frequency times wavelength, is speed, and the speed is c. And you can solve that for the frequency, and you can then plug that in. So take that, plug it in right here. And when you do, you get hc over c, and the c's cancel, and you get p is h over lambda. The reason this one is relevant is that this last one here holds for electrons, neutrons, protons, and U. And the others did not. So with De Broglie, we're going to find out that this is a universal statement for everything. To have momentum is to have a wavelength. So that equation is something that should be in your mind. That's an equation you should put away permanently, because we're going to use it a lot. It's important for the uncertainty principle. It's important to explain the Bohr orbits. It's important for lots of things. So this one is one we want to put in our mind. It's universally true, even for things that you have rest mass, and even for things that do not obey E equal h nu. It's also true for the photon, which is how we got it, but it's true for everything. And the last thing that I put in that notes is you can write it one more time by doing a little bit of algebra, which would seem maybe not to be much use, but turns out it is. And that's if you come back up here and you say, hey, lambda, the wavelength, can be related to the wave number in physics 2, where the wave number k is 2 pi over lambda. And if you do that, and you do a little manipulation, as I've done here in a series of steps, you can say, okay, I'll multiply by 2 pi on the top, multiply by 2 pi on the bottom. 2 pi over lambda, that's k. H over 2 pi, I'm going to give it a new name. H bar. It's still a constant. It's Planck's constant divided by 2 pi. Why would I want to do that? Because it turns out that k shows up in quantum mechanics every time you take the Fourier transform of position. It's called a reciprocal space. For physicists, when they're working with stuff, they're usually working in either frequency and time, those are reciprocal spaces, or they're working in position and k-space. Those are reciprocal spaces. So you will find that all the operators and such in quantum mechanics are written in terms of k rather than p. They just differ by this constant. But because we spend so much time in k-space, it's useful to know the relation between them. All right? So, equation D and equation C are real useful for the future. We're going to deal with them a lot. For most of the equations dealing with photons, equation A is probably the easiest way to get around. They all three can be attained just by doing algebra. All right. So what can you ask out of these type of problems? Well, you could do something really simple. Like I said, you could say, hey, you got a photon of 2 MeV. The easiest way to do that is P is E over C. Just treat it like it is. Really easy, easy, easy. You can also ask, what is the wave number? Now the thing gets a little bit harder, okay? So let's look at a couple of things. First, you're going to need to find P. Well, that's E over C. So E is PC, which is HC over lambda. So it's relatively easy, using P as H over lambda, to go ahead and find E. You also could have used E is equal to H bar K times C, which is HC times K over 2 pi. Why do I like doing that rather than just plugging in some numbers? I like that because I know that number. 1240 EV nanometers. So if that thing's an MEV, that's 1240 MeV Fermis. And I can easily rearrange and multiply by 2 pi and I'm done, and I don't have to do all those conversions. That's why I like to stay in this thing. I like to get H and C together whenever. I don't know H bar off my head. I know H bar is H over 2 pi. So I prefer to stay with HC. If you do that, it will be quicker. If you don't, you're going to get into converting things all over the place. MEVs to joules and H's to joules seconds and whatever, and C's and meters per second, and it's just going to take you a lot longer. So take this guy, do like this, and you get K is 2 pi, 2 MeV, 1240 MeV Fermis. The MEVs cancel. 4 into 1240 is 310. Punch calculator. Relatively easy way to do a calculation. All right. So try to stay out of SI units whenever possible, and whenever possible, try to use these relations to try to get HC wherever you can. You can find the wavelength, you can find the wave number, so forth, as long as you stay up there. Next section. The next one has an interesting historical thing, and you guys, at least at Tarleton, are going to have to do it, and that is the Compton effect. If the photon has energy and momentum, you can think of it as a billiard ball. There he is, right there. And you can shoot that billiard ball at a material, and that material will have electrons. And when it strikes those outer electrons, not the inner, when it strikes the inner electrons, what tends to happen is it either gets some excitation, or more likely, it's swallowed and the electron is ripped out, and you get the photoelectric effect. But if you hit the outer electrons, then the photon will bounce off of it. So here's my photon again. But it'll have a new energy, a new momentum, and therefore a new wavelength, a new frequency. And the electron will be given kinetic energy and come off at some other angle. This is elastic scattering. It must conserve linear momentum, and it must conserve relativistic energy. Now the momentum in the x direction was the momentum this photon had coming in, plus the momentum of the electron here, times how much is along this way, this part. And that's the adjacent side of that angle, so it's the cosine of theta. Plus the amount going this way times how much is along this way. That's the cosine of v. Along y, there was nothing along y. So this part here, which is the sine, has to exactly cancel this sine down here. If you only threw one photon and you caught one electron, this would be easy. But that's not what happens. What happens is a bunch of photons come in. They go in all different angles. And most of the time, these electrons never get out of the material. So we actually need to eliminate everything about this electron because we can't detect it. In other words, we have these two equations and the energy equation, and we need to solve them. And the only things we can have at the end are the energy or the wavelength coming in, the energy or wavelength going out of this photon in this one angle, because that's all we can measure. We can't see the electrons at all. Well, that's a nice demonstration of how to do a bunch of algebra and trigonometry, and I'll leave that for you to read in the book. All right? But if you do all of it, here's what you get. the wavelength that comes out will be longer than the wavelength that it started with. Why? It has less energy now than it had before. It will be related to what it hit. And what it hit in this case was an electron. So if you do all the algebra, you find this H over MC. By the way, I don't like that. I think I'll multiply by another C. Put a C on top. And now I got HC, and I got the M of an electron C squared. Now what do you call MC squared? Yeah, that's the rest energy. That's 1240 MeV Fermis, and this happens to be 0.511 MeV, and I can cancel it, I can find this number. And it's not 2.46, it's 2.43 picometers. Now, if you struck something other than an electron, and by the way, there are homework problems in the text that do, then this mass down here will be something different. And it will change this value. Something different will go here. When Compton did it, he was looking at cosmic rays as such bouncing off of electrons. And so he got his name on this constant called the Compton wavelength. It is basically the wavelength of the electron, which is hc over the energy of the electron. What you do here is that for an angle, and for a given land of a photon, you can calculate the new wavelength the photon scatters. If you know the new wavelength of the photon, you can calculate its new momentum. If you know the new wavelength, you can calculate its energy. If you want, and you're given energies, you could take each one of these guys and divide by hc. And if you do that, this becomes lambda prime over hc, that's 1 over the new energy. This one is lambda over hc, that's the incoming energy. And this hc cancels, and you're left with the rest energy of the electron. These are two totally equivalent ways to do it. Homework problems tend to give you the lambdas. People who do this most of the time in the real world have energy detectors. They tend to work with this equation. What is not easy to do is to get the kinetic energy of the electron in one step. Don't try it. Find the energy of the photon. Maybe that's 500 keV. Find the energy of the photon that goes out, 300 keV. Then that guy is 500 minus 300 is 200. Do not try to solve him directly. Solve for the photons, subtract the energy, and use energy conservation. It's the easiest, quickest way to do it. Okay? I wrote you some things down in your notes about facts that you should get out of the equations from your reading. But pretty much what I've already told you. The wavelength of scattering is always larger than the wavelength coming in. That's required for conservation of energy. The energy of the photon going out is always less than the energy of the photon going in. The kinetic energy is the difference. You might wonder about, what about the rest energy of the electron? It was accounted for here. I know I didn't write it. I could have. There had to be an electron before they collide. By the way, there has to be an electron after they collide. They cancel. The electron exists before the collision, the electron exists after the collision. So why put it down? It is really counted. All the energy before has to equal all the energy after. If there were new particles created, there would be new rest mass energies over here. There are no new particles created here. Yeah.
Oh, no, that's right.
You're stretching your arms. Okay. By the way, that's how to calculate the maximum kinetic energy. That's not any fun. All right.
That's a problem.
So let's see. I had a test your knowledge problem on that thing as well. It was this one. A beam of photons is directed upon a target. What is the wavelength of the incident photon if the photon scattered at 45 degrees and have a wavelength of 2.2 picometers. So let's see, we have lambda prime minus lambda, is lambda c, times 1 minus cosine of theta. We're using phi here. I don't remember which. We're using phi, I'm sorry. So phi is 45 degrees. Lambda c is 2.43 picometers. Lambda we don't know. It says wavelength of incident photons. Lambda prime is 2.2 picometers. Easy calculation, okay? Lambda will equal lambda prime minus lambda c, 1 minus cosine of phi. So let's see, I have 2.2 picometers minus 2.43 picometers times 1 minus cosine of 45. And all you need to do is just punch in the calculator. So let's make sure that my cosine of 90 gives me 0 like I expect. It doesn't. So let's see. No, not in degrees. It's 1 minus cosine of 45 is that, times a minus 2.43. And then I want to add that to 2. 1.49 picometers. Now you could also be asked what's the energy that it had, okay, if you want. It says what's the maximum energy that an incident photon can give to an electron? Okay, now here's the point. The maximum energy, I need to know the angle at which it scatters to find that. So if you have a billiard ball, like a billiard ball like this, there's Mr. Electron. And here comes Mr. Photon. In like that. The maximum energy is going to occur when this guy goes this way. So if he goes this way, this photon, which I'll call prime, is going to go that way. So maximum energy occurs when you have 180 degree scattering. If you played football in the state of Texas, you know these facts. When you come in and get hit by a person, a linebacker, that's not where you get hurt. If he grabs you and hits you, that's not where you get hurt. Where you get hurt is when you come in and get hit and you bounce backwards. All right, that's when maximum momentum transfer occurs. That's when maximum energy. When you get a guy cleating, you hit him, blindside, he bash you backwards. That's when they really get hurt. Same thing here. This guy gets maximum thing when this angle is 180. So we know that phi is 180. Now we also know from this problem what the incoming wavelength was. First thing we need to do now is calculate the new wavelength for 180. So lambda prime is equal to lambda plus lambda c, 1 minus the cosine of 180. What's cosine of 180? -1. So you get 1 minus a -1. This whole thing is 2. All right, it looks like we're about to end, so we'll see you next time.